All right, let's talk about a big idea, which is what is algebra? And then let's take a look at some small aspects of this and just do some quick review on some things that we've kind of been leaving in the background, which is basically our rules of how we're doing things, especially with exponents, which is where things can kind of get tricky sometimes. So big picture, what's going on? Well, we're setting up equations of symbols, right? So y equals mx plus b is an equation that we should all feel pretty comfortable with. But what's m, what's b, what's y, what's x? All four of these are just placeholders. We are just putting them on the page and we're manipulating them following specific rules because we know whatever the value of m is, it's just as true that if we rearrange this equation, no matter what the value of m is, the manipulations we make are going to be valid as long as we're following our basic rules. So, what are some of our basic rules? And let me also give you some hints along the way. So, let's just look at exponent rules. A lot of these rules you probably are already familiar with, so we don't really need to go through them too much. Exponent, t becomes an e. And we'll take a quick look at logarithms. And what I find helpful with a lot of these things is just kind of thinking of small numbers in the background. So 0 and 1 can do some special things, but 2 and 3, especially for exponents, are really nice, easy numbers to use. So if we've got a rule like, what is x to the a times x to the b? Well, let's say we're thinking about 2 to the 2 times 2 to the 3. Well, that's just 2 times 2 times 2 times 2 times 2. Well, that's just 2 to the 5. So x to the a times x to the b, we can say that that's going to be the same as x to the a plus b. That's not too bad. If we say x to the a over x to the b, well, this, it turns out, is equivalent to x to the a times x to the minus b, right? A minus exponent is the same as just the reciprocal with a positive exponent. So in this case, this is going to give us x a minus b. And just to verify there, we could again use these two. We could say 2 to the 2 over 2 to the 3. Well, we're going to end up with 2 times 2, 2, 2, 2. Cancel, cancel, and we're left with 1 over 2. Right? Again, these little numbers I find really helpful. I find it really difficult, for example, to remember, am I supposed to be doing it like this? Or what about if it's x to the a to the b? Right? In that case, now we might think of x to the a as 2 squared. So that's what? 4. To the 3 is going to be 4 times 4 times 4 times 4, which is the same as 2 times 2, right, for each of those. So x to the a to the b, well, what do we get? We end up with, in this case, I say shouldn't have been 4 fours. Sorry, there should have been 3 fours. So we end up with 3 times 2. So this is going to be x to the a times b. And a lot of the times, since we use x especially so much, ab is better than a times b, especially when we want to save that as a symbol, right? We just recognize a times b, a times b. This is really the same thing. This is a subjective inequality. All right, so we've got a handful of these. We have also implicitly seen here another important rule, which is x to the minus a is the equivalent of 1 over x to the a. We've seen an exponent of an exponent. We've seen 2 exponents being multiplied is actually the same as adding the exponents. That's basically the underlying reason that logarithms were so important before computers made it easy to do fast multiplication. Multiplication when you can do it fast is great, but if you are working without a computer, it's easier to add logarithms, where you look up what is the log value of some number and add it to the log value of some other number based on their relations. All right, so what have we seen? Multiplied leads to add. Negatives are the same as a fraction. An exponent of an exponent is a multiplicative thing. Let's take a look at some of the logarithm rules. Right, so basically, if we put these guys together in different ways, actually, you know what? Here's one that we should talk about before we move on, which is x to fractional powers. X to the 1/2 is just the square root of x. X to the 1/3, that is the cube root. Right, let me make sure I'm remembering that correctly. Now, whatever it is. I lost my page in my notes, so we'll say it's the cube root. But sometimes, especially when we're looking at derivatives, it's going to be a lot easier to think about this as x to the 1/2 than as this radical term. It's just going to be convenient based on one of the rules that we're going to use. All right, so let's look at the basics of logs. All right, and logs are basically the other side of exponents. And you know what? I'm going to add a video to this playlist from 3 Blue 1 Brown, which actually I mentioned in a previous video, which is the triangle of power. So actually, let me really quickly, triangle of power. I'm going to try and replicate what he's talking about there, but it's going to be a lot easier if I've got it on my screen. So he gives an example, 2, 3, 8. So what's going on here? Well, 2 to the power of 3 is 2 times 2 times 2, which is 4 times 2, which is 8. Right? So here we've got a base, we've got an exponent, and we've got a final answer. Now, another way that we can express this relationship, that 2 to the power of 3 is equal to 8, is we could say log base 2 of 8 is equal to 3. Right? So this is just saying 2 to what exponent gives us this number. We use that in the time value back here. Where did we lose it? We used it over here, right? So log base 1.1 of 1.1 to the t, right, was basically another way to say, let's try and find what does t need to be to double the value of our investment at a 10% interest rate. Right, so using log and a base, in this case log base 2 of 8 gives us 3. Right, so another way we could think about that is 2 to what exponent, or sorry, 2 to some exponent. Yeah. Let's use the triangle of power here. 2 and 8, where we're saying log base 2 of 8 is asking what exponent on 2 would we need to get to come down to this 8. So we're just using this bottom part of the triangle here, where we're using this part of the triangle here, and then that leaves the other part of the triangle, which is the cube root of 8, which again is just saying what radical do we need to express the relationship of 3 and 8, and this radical is going to give us back that 2. So that's the general relationship. I know that that doesn't fit neatly into our Paleolithic brains, so practice helps, and Khan Academy is going to be a good source of practice on this, and also just checking out the Triangle of Power video. So what can we do with these logarithms? Let's go ahead and just lay out some simple rules. I don't normally spend a whole lot of time on the logarithms, but as long as we're laying out videos in advance, we might as well, right? It's not too difficult. So if we've got log base a of xy, this is an a, log base a of xy, this is the same as log base a of x plus log base a of y. Right? And again, that is basically coming back to here. We're saying to get something, right, we've got some weird exponents. And in this case, let me lay this out the way that the book I'm looking at uses this. They say y equals a to the x. So in this case, we're multiplying this, and we're using this base. And this is basically coming out to tell us that the logarithm of some product is just the sum of those logarithms. So we want to know what is x times y. Well, we could just take the log of both and add them together. This is basically how they used to do difficult math before computers. They'd have these big books of logarithms because it's easier to add than to multiply. Next rule, log base a. So if we've got some log base a of a quotient x over y, in this case we can take this log and we can subtract this log. Right, so that again has to do with these negative exponents, and we're basically getting the same relationship as we've got here, just in a logarithm, so that we're not dealing with, say, messy exponents or messy multiplication. Another rule, log base a of x to the n equals n times log base a of x. And this is a really handy tool. This allows us to bring exponents down. This is really useful if you want to go into the proofs about things like the generalized power function rule, which you'll see in the coming weeks. You don't need to get into that to use it, right? You could be a lazy economist and trust the mathematicians, but this rule is what's allowing that to happen. And this basically is saying we take a log of some term to an exponent and we can bring that exponent down. Let me use green just to show this exponent is flipping down here. So we still got log a of the base, but the exponent comes out, and now we've got something where, coming back to that question we asked of what would r have to be to make it so that the $2 trillion in 30 years is worth $1 trillion now. In order to solve that, taking the log allows us to bring that t down. So let's go ahead and actually set that up. So we're saying future value equals twice that. So if we say, oh, we're doing logs there already. So we're saying 2 equals 1 times 1 plus r to the power of 30. And then we could just take some log of both sides, and that's going to tell us that 30 equals whatever base log you've got of 2 divided, again, same log base of 1 plus r. That ratio equals 30. So then we can rearrange and solve for r, right? I'm not going to go through and try and solve a logarithm live on camera because that'll take too long for me to figure out what I've forgotten about math, but we can use that relationship and get that much closer to a solution. And finally, coming back into the part I'm probably least comfortable with, log base a for the nth root of x equals 1 over n of log base a of x, right? So this is really just the exact same thing as this. So if n, for example, this n equals 1/2, then this is the same as saying log base a of x to the 1/2 equals 1/2 log base a of x, right? And this is just the square root of x, or I got off the screen there. The square root of x, this is exactly the same term. Using that logarithm, we can bring that exponent down and we can isolate that x term, which we might want to do depending on the model we're looking at. All right, so that was a little bit of a scattered look at some rules of exponents and logarithms. In practice, you just Google rules of exponents if you're forgetting, but plugging in simple numbers like 2 and 3 can help to verify when you do feel comfortable. Or if you've got access to a computer, you just use the logarithm function in your spreadsheet or R or Google, right? Google's pretty good at calculating things like this for us also. But like I said, in practice, you Google it, and if you see a result from, say, Purple Math, which is a popular math education site, or Khan Academy, or wherever, then you say, okay, well, let's just look it up there. In practice, you're going to forget this stuff. But that's why we're doing this class the way we are, with open book quizzes. So be ready for that, but it is good to practice just to feel comfortable with this beforehand.